Hello everyone. Welcome to Hydropower. Today we will be discussing about the use of extreme and long-term hydrological data. So, let's start with the introduction of extreme and long-term hydrological data. Extreme and long-term hydrological data serve crucial roles in understanding water systems and making informed decisions. Both extreme and long-term hydrological data are essential for effective water management, infrastructure design, disaster preparedness, and environmental conservation. They provide insights into the behavior of water systems under various conditions, helping society make more resilient and sustainable decisions. Here's the brief description on how they are used. Extreme hydrological data refers to information about rare and intense events in the water cycle, such as floods and droughts. These events can have significant impacts on water resources, infrastructure, and the environment. Here's how extreme hydrological data is used. Flood risk assessment: analyze historical extreme flow events to assess flood risk and design effective flood control measures and infrastructure. Emergency planning: use extreme data to develop early warning systems for potential flood or drought events, allowing timely response and mitigation. Infrastructure design: design dams, bridges, and other structures to withstand extreme flow conditions, ensuring their safety and longevity. Insurance and risk management: insurers use extreme flow data to assess flood risk and set insurance premiums for properties located in flood-prone areas. Environmental impact studies: study extreme flow events' effects on ecosystems, habitats, and water quality to mitigate environmental damage. Example of extreme hydrological data: for a specific flood event, at ABC River flood dated August 15 to 18, 1993. Extreme data recorded. Peak discharge: the maximum discharge rate recorded during the flood event was 1,200 cubic meters per second. Total precipitation: over the 3-day period, the region received a total of 250 millimeters of rainfall. Rising rate: the river's water level rose by 3 meters in just 6 hours at the peak of the flood. Flood duration: the flood event lasted for approximately 72 hours before water levels began to recede. Affected area: the flood inundated an area of 10 square kilometers, affecting several villages and agricultural. Now let's discuss about the long-term hydrological data. Long-term hydrological data provides a comprehensive view of water cycle patterns over extended periods. Here's how it is utilized. Climate change analysis: long-term data helps detect trends and changes in hydrological patterns due to climate change, aiding in adaptation strategies. Water resource planning: plan sustainable water allocation for agriculture, industry, and urban areas based on long-term average flow rates. Drought prediction and management: analyze long-term data to identify drought-prone periods, assisting in drought prediction and water conservation planning. Erosion and sedimentation studies: long-term data helps study riverbed erosion and sediment deposition patterns, guiding erosion control measures. Ecological studies: study long-term changes in stream flow to understand their impact on aquatic ecosystems and biodiversity. Reservoir management: manage reservoir levels and releases over the long term, balancing water supply, flood control, and energy generation. Example of extreme hydrological data. For a specific flood event, at ABC River flood for time period, 1980 to 2020. Parameters collected. Daily stream flow: recorded discharge at a monitoring station along the ABC River. Monthly precipitation: measured rainfall at a meteorological station within the basin. Annual snow melt: estimation of snow melt runoff based on snowpack measurements and temperature data. Annual evapotranspiration: calculated evapotranspiration using weather data and land cover information. Water quality parameters, data on water temperature, pH, dissolved oxygen, and nutrient levels, collected at regular intervals. Thank you. See you in next video.